right, so today's lesson's our last lesson about solutions and creating solutions and things like that. So, and then we were going to move on to talking about bonding a little bit. So first of all, let's go back to what we were talking about, I believe, in our last video where I kind of skipped over this part. So today we're going to talk about how you make a solution. So when you think about making a solution, there's three things that have to happen. Two of those things require energy. One of those things releases energy. So think about taking some salt or some sugar and dumping it into water. There's two things, again, that require energy, okay, that require you to break some attractions between particles, okay? And again, and I mentioned this just briefly, but those are what are called endothermic processes, and those are the ones that require energy, okay? So the two processes are the water basically has to make space for the sugar, let's just use sugar, for the sugar particles to fit in. So the water particles have to break apart from each other. Again, that's an energy requiring process. Okay? And then the sugar molecules also have to break apart from each other. So you don't see, once you've dissolved the sugar, you don't see the sugar in there anymore. That means that the particles, the molecules of sugar have broken apart from each other. Okay? But then the sugar and the water make attractions to each other. And that is the last step. That is what's called the exothermic process, and that releases energy. So sometimes when you dissolve things, that process overall will require energy because the two steps that require energy are greater than the one step that releases energy. Sometimes when you dissolve things in water, or sometimes when you mix two things together, it releases energy. It will actually feel hot. That's what this process here is a process that feels hot. Okay? And so when that happens, again, that means that this part right here releases a lot more energy than this part right here requires. So depending on the magnitude of each of those values, if this number is really, really big and these numbers are smaller, then overall it's going to release energy and it's going to feel hot. Okay, think about like when you break like one of those, like on the 4th of July, when you break those, the light pack things and all of a sudden they light up, okay, that is an exothermic process. That's releasing energy, not in the form of very much heat, but obviously in terms of light, okay? And then there's ice packs and heat packs that when you break things, they release a lot of heat and then you put it on your sore shoulder. Again, those are all exothermic processes. Things that feel cold are things that require energy. They're absorbing the heat from your body. If you put an ice pack on you, that heat is being absorbed from your body into that. Okay, and we're going to talk about endo and exothermic in way, way, way more detail later on this year when we get to Unit 5. Okay, when you make a solution, so we're talking about putting sugar in water, it doesn't matter what. Okay, but when you're going to make a solution, the first thing that you have to figure out is you have to figure out how much of that sugar, or in this case, Na3PO4, you're going to need. So if I'm going to make 250 milliliters of a 0.6 molar solution of Na3PO4, the first thing I have to do is I have to figure out what mass of sodium phosphate do I need. And to do that, we know that we take the concentration and we multiply by the volume. Since molarity equals moles over liters, and we know the molarity and we know the volume, we can move the volume over to the other side, and that will get us to moles. We'll multiply molarity times volume. So moles equals molarity times volume. Once you have the moles of sodium phosphate, then you need to use the molar mass of sodium phosphate and convert to grams. Okay, and so once you have the grams, then that's where you're going to start with. So you'll notice in my steps here, and this is how you should write it out if they ask you to, because again, why am I teaching this? Because I've asked this question before. Okay, so you're going to measure out the 16 grams and you're going to show the math on how to do that. So you're going to show 0.600 times 0.250 liters, and that's going to equal a certain number of moles. And then you're going to show in 1 mole, I think real quick, I'm trying to do that in my head, I think it's 164 grams is the molar mass of Na3PO4. And I didn't actually do it, obviously, but I think that number comes out to be right around 16 grams, okay? So, and then you add that, oh, I'm sorry, it's NaOH. Sorry, I'm still reading this part up here, but then it says down here. So, really, let's see. I'm not sure why I switched there. So, in order to prepare a 2 molar solution of NaOH, and again, it does. I don't say how much. They really need to say, like up here, I did say a 0.600 molar of and 250 milliliters. So here, I really need to say, you can't just say a 2 molar solution. It really needs to say 100 milliliters of a 2 molar solution. Okay, so let me show that math correctly again here. That would be, if I was doing this solution up here, that's exactly how you would do it. But since clearly I changed it, okay, so I would take that concentration, I'm going to multiply by its volume in liters. And the only reason I know it's 100 milliliters is because I looked at my answer down here and it said 100 milliliters. Okay, so 200 times 0.1 is 0.2 moles of NaOH. And NaOH has a molar mass of 231640, so 1 mole, 40 grams. And 40 times 0.2 is 8 grams. So again, clearly there's something wrong here. I need to go back in and fix this whole thing because I didn't put the volume. I don't have the right mass there. It should be 8 grams. Anyway, you get the point. You get the mass of the solute. You add it to that volumetric flask. Always use a volumetric flask, and clearly it needs to be 100 milliliters. And then you get up close to, so add enough water to bring the volume up to the line on the flask. Again, you want the bottom of that meniscus right on the line. You could even talk about using a dropper to get that last little bit. Okay? All right. So, let's see here. So it looks like, holy cow, I feel like I needed to start this whole thing over. Anyway, so in example 1, this is just an example question, okay? And clearly they screwed up because when I did the math, I did not get the same number as them. So in part A, let's actually get to the question now. The chemical quantities used in the procedure do not produce 2 molar NaOH. Describe specifically how they should be changed in order to produce 2 molar. So if I'm going to try to produce 2 molar and I have 100 milliliters, then obviously that only requires me to have 8 grams, okay? And here they're saying 16 grams. So if I had 16 grams, that's going to produce a 4 molar solution. Obviously, I've got double the mass, so I've got double the number of moles, okay? So in order to do that, how would you get, specifically describe how you would change that? So instead of 16 grams, basically you would say in step 1, use 8 grams of NaOH, not 16. Okay, and that is very specific. You're telling them exactly what to do differently. Okay, part B says another student is preparing 2 molar NaOH solution using the actual correct chemical quantities, but notices that some dissolved solid remains at the bottom of the flask. So not all of it dissolves. So if you use that 8 grams or whatever, and not all of it dissolved, is the concentration in the solution greater than, less than, or equal to 2 molar? Well, you had 8 grams. Let's say you only put in 6. Well, you've put in 8, but only 6 of it dissolves. Okay? Do you have a 2 molar solution? Of course you don't. You're not quite there yet. To get to 2 molar, you have the correct volume, but you don't have the correct number of moles of the solute. So it's moles over liters. And again, to get that to be correct, you would have to have all 8 of those dissolved. So therefore, it is less than. And again, you would describe that by saying that because not all of the NaOH is dissolved, that the concentration must be less than 2 molar. The moles of the solute is less than what it should be. Okay, and the last thing, let's see if I can not screw this one up, is when you combine two solutions, okay? If you take two different solutions with two different concentrations and you put them together, basically you've got a new number of moles and you've got a new volume. And typically what they'll say is the volumes are additive, which means if you add the two volumes together, it gets to, you just add the two together and you get a new volume. So in this case, for example, what we would have to do is we've got two different solutions. We've got this solution and we've got this solution. Okay, they're both of potassium chloride, and we want to know what's the molarity of this combined solution. So it's definitely going to be somewhere between 0.125 and 0.225, somewhere in between there. Okay, this one's going to go up a little bit. This one certainly is going to go down a little bit. Okay, but we have different volumes too. So we can't just say, well, let's find it right in the middle. If the volumes were exactly the same, then we could go right smack dab in the middle. But we're not. So the most secure way to do this is to take each of the concentrations and multiply by their volumes. So I'm going to do that for both of these. 0.225 molar times 0.075. Okay, and I'm going to get a number for each of those. So 0.125 times 0.050 equals, and again, I'm not worried about significant figures here. So 0.00625 moles of KCl in this one. And for the other one, 0.225 divided by 0.075 equals, I feel like I screwed up there. Oh yeah, I hit divided by, times 0.0 is 0.016875. So all total, how many moles of potassium chloride do I have? I don't know, but I'm going to add them up. So that plus 0.00625 equals 0.023125. Again, not worried about significant figures. Okay, so 0.023125 moles of potassium chloride is how many moles I have all total between this solution here and this solution here. Okay, and so what's my concentration of that solution? Well, now I just take my total moles of the solute, and again, I add those two volumes together. So 50 plus 75 is 125 milliliters, which is 0.125 liters. So I'm going to take my number that I have in my calculator, I'm going to divide by 0.125, and I get a final answer of 0.185 molar. Okay, so when you combine two solutions together, just treat them separately. Okay, figure out the moles of both, add them together, and then divide by that new volume.